In Unit 2, we talk about how to solve larger systems of linear equations. I will show you what I mean. Okay. The definition is here. The definition is here. Okay. In the definition, I'm trying to define what we mean by a linear equation. A linear equation. Okay. A linear equation. The definition is a little bit abstract. I will show you what I mean. Okay. I'm going to write something here. So now let's say if you have two unknowns, two variables, a equation like that is called a linear equation. So now let's say 2x1 and then plus 3x2, okay, and then plus 5x, so maybe 3 equals 10. That's a linear equation. Okay. For the linear equation, I'm going to tell you some terms, some names. Okay. In the equation, we have three unknowns. The unknowns are also called variables. Okay, we have three unknowns. In most cases, in this course, I'm going to call them unknowns. Okay. We have three unknowns, and the numbers before the unknowns are called coefficients. I said coefficients. I'm going to write something down. Okay, coefficients. Okay. So now let's say the coefficient of x1 is 2. Okay. The coefficient of x3 is 5. And if we put the equation in standard form, we put the constant to the right of the equation. 10 is the constant term. Okay. Again, in a linear equation is an equation strictly in that form. We use x1, x2, xn, and so on for the unknowns. We use a1, a2, and an, and so on for the coefficients. Okay, and we always put the constant term to the right-hand side of the equation. And by the way, the definition is on the course manual. Okay, you do not have to copy. You could take a picture if you want. Okay. Now remember the term, what we mean by coefficients, what we mean by constants, okay, what we mean by unknowns. Okay. The equation is called linear, so because you cannot have something like x1 squared, x2 squared, cos of x3, sine of x3, and so on. Okay, a linear equation is an equation strictly in that form. Okay. I think in high school, if you have a linear equation in two unknowns, we can talk about the graph of the equation. It's a straight line. I believe you can remember that. Okay. And also in some cases, if there are not too many unknowns, we could use x, y, and z for the variables, for the unknowns. So now let's say this equation, so now let's say 5x and then plus 3y equals 1. It's also a linear equation. The full sentence is a linear equation with two unknowns. Okay. For any equation, we can talk about the solution to the equation. Okay. I think it's on the next slide. Now we're talking about what we mean by the solution to I haven't given you the definition of what we mean by a system of linear equations. A system consists of many equations. So now let's say in this case we have a system. Now remember how we call it. Okay. In this case we have a system of two linear equations. So there are two equations, right? In two unknowns. I want to repeat. This is if you put the two equations together, you treat the whole thing as a whole. You treat two equations as a whole. We call the whole thing a system of linear equations, a system of two linear equations in two unknowns. The two unknowns are x and y. Okay. What we are concerning is for any linear system, what we are concerning is the solution. What we mean by the solution to an equation. A solution is are the values of the unknowns satisfying all equations. So now let's say for that system, if x value is 1, y value is 1, it we have a solution to the system. Okay, so because if you plug x value of 1 and y value of 1 into that equation, 1 plus 1 is equal to 2, right? That equation is satisfied. And also 1 minus 1 is 0. That equation is also satisfied. Okay. So I just told you what we mean by the solution to a system. A solution to a system of linear equations is a solution to all equations. Okay. Simple enough? Okay, now I'm going to move to the next slide. So any questions so far? So just some names. What we mean by a system of linear equations. What we mean by a solution. Okay. Okay, we'll move on. Okay. The new thing we are going to learn is so eventually we are going to talk about how to solve a larger system. Now look at the system in here. It's now let's recall how we call it. Okay, so here we have a system of 3 linear equations in 4 unknowns. I want to repeat. On the screen you have a system of 3 linear equations in 4 unknowns. Okay. So eventually we are going to learn actually in less than 2 weeks. In less than 2 weeks, you are going to be able to learn how to solve a larger system like this. Okay. By solving a linear system, you need to answer 3 questions. In some cases, a system does not have a solution. Okay. Now, for instance, if you have a system like this, so now let's say x plus y equals 1, and then so maybe x plus y 2x and then plus 2y so equals 4. That's a system. That's a valid system. Okay, but that's a system having no solutions. I will tell you why the system has no solutions. Okay, the system is actually equivalent to the following system. I'm going to use a notation like this to denote 2 systems are equivalent. Okay. That system is equivalent to a new system. By equivalent, I mean the 2 systems have the same solution. If that's the case, then we say the 2 systems are equivalent. Okay. I will write a new system. Okay. So now let's say the first equation is the same. I'm going to copy that. X plus y equals 1. The second equation is essentially the same thing as, let's say, x plus y so equals 2. Now I want you to recall what we mean by a solution to a system. A solution is a solution to all the equations in the system in general. Okay. The new system does not have a solution. I believe you can see why. For any 2 numbers, if the 2 numbers add up to 1, the 2 numbers cannot add up to 2, right? I'm trying to say there are no values of x and y satisfying both equations. So that system has no solutions. Okay. I'm trying to tell you it's possible for a system to have no solutions. Did that make it clear? A system can also have many solutions. I'm going to make the next point. Okay. A system can also have many solutions. Yeah, probably I'm going to use that slide. Okay. So how about we have a system like this? So now let's say a system. So now let's say x minus y so equals 0. If I have another equation, now let's say 2x So minus 2y so equals 0. That's also a valid system. Okay, that's also a valid system of linear equations. You check the definition. We have two linear equations. We put the two equations together. We have a linear system. Okay. Can anybody tell me at least one solution to the system? I'm going to open my chat. Okay. On the other screen. I think I had my chat open. Can anybody tell me at least one solution to the system? No. By one solution we mean a value of x, a value of y, satisfying all the equations in the system. X value of 1. So now let's say y value of 1. That's a solution to the system. Okay. Again, a solution to a system is a set of numbers, a set of values of x and y satisfying all the equations. You see x 1 minus 1 is equal to 0. 2 minus 2 is equal to 0, right? That's one solution to the system. Okay. Can anybody tell me another solution? 3, 5 is not good. 3 minus 5 is equal to 3 my x value of 3 and the y value of 5 is not a solution to the system. Why? So because 3 minus 5, if you replace that x with 3, if you replace that y with 5, then 3 minus 5 is not 0. That's not a solution. Okay. Three five is not a solution. Anybody want to tell me another solution? Another solution consists of two values, a value of x, a value of y. So just write two numbers. The first number is a value of x. The second value is a value of y. Yeah, 2 is good. 2 is good, easily. X value of 2, y value of 2 is another solution. Okay. Any more solutions? 3 is also good. 3 is also good. Okay. I'm trying to say, I believe now you know the meaning of what we mean by the solutions. Now you can see the system has many solutions. As long as the two numbers are the same, it is a solution to the system. 4 is good. 23 is good. Yeah, that's good. Okay. So the system has many solutions. Actually, the system has infinitely many solutions. As a matter of fact, later on you are going to see. For any linear system, there are only three cases. One case is the system has a unique solution. By unique, I mean one and only one solution. That one has only one solution. Okay. We say one solution, we mean a pair of values. We do not see two solutions. We see it's one solution. One solution is a value of x, a value of y. That's one solution. Okay. For any system, again, we are concerning what is the solution to the system, or what are the solutions to the system. Okay. For any linear system, there are only three cases. One case is the system can have a unique solution, one and only one solution. The system can have no solutions. The system can have infinitely many solutions. Okay. I think we have seen all the cases. Actually, it's true in general for any system. No matter how many equations, no matter how many unknowns, there are only three cases. Okay, a system can have one only one solution, many solutions, or no solutions. Okay, I think you got the point. Okay. Again, our job is to solve a system. By solving a system, you need to be able to answer three questions. Okay. The first question is: does the system have a solution? Does the system have at least one solution? In some cases, it has no solutions, right? The second question we are going to be able to answer in less than 2 weeks is uh, how many solutions? How many solutions? If the system has a solution, then there are two cases, right? Either a unique solution or many solutions, infinitely many solutions. Okay. And the third question is, what are the solutions, or what is the solution if the system has a unique solution? Okay. Okay. So that's the thing. Any questions so far? If you don't have any questions, we'll start to do some handout questions. So basically, the from Unit 2, I covered some definitions and made some comments on the definitions. Okay. Now we're going to do some questions using the definitions. If you want, you can open handout 1. Handout 1. I told you to download 2 files, right? Open handout 1, please. We'll go over some questions. So basically, we're going to build some ways, methodology, how to solve a larger system. Okay. Now we need to talk about what we mean by the augmented matrix associated with a system of linear equations. Okay. Augmented system. Okay. I will show you the meaning. I will show you this meaning. Okay. Now, for instance, if we are trying to solve a system like that, in the system we have 3 equations, we have 4 unknowns. Again, the name of the system is a system of 3 equations with 4 unknowns. Okay. And then we're going to represent the system using something called a matrix. In this course, you are going to see the term matrix over and over again. Actually, some people just call this course the matrix algebra. Okay. Matrices are super important in this course. Okay. The first term associated with a linear system we're going to introduce is what we mean by the matrix of coefficients. We are going to use the term later. Okay. And by the way, to write a matrix, you need to use either round brackets or curved brackets. Sorry, do not use curved brackets. You need to use either round brackets. So in this case, you have a round bracket, right? Or square brackets. So by that, I mean the brackets is something like this. This is the case we have a round brackets. That's the case we have square brackets. Okay. Again, to write any matrix, you need to include some numbers in either round brackets or square brackets. Okay. You have to write brackets. Okay, now let's take a look at how we form the matrix of coefficients. Okay. These are the numbers coming from the coefficients of all the equations. Now look at the first row. The first row has all the coefficients of the unknowns in that equation, right? You see the coefficient of x1 is 1. It gives you that 1. Okay. Now let's say the coefficient of x4 is -3. It's -3, right? It gives you that coefficient. It will give you that number. Okay. Again, each row in the matrix corresponds to an equation. So because in the system we have three equations, right? So correspondingly in the matrix we have three rows. Okay. So temporarily matrix of coefficients is not so important. So temporarily we concentrate on what we call augmented matrix. In the augmented matrix, in addition to the matrix of coefficients, there's one additional column. The numbers in the additional column are from the constant terms. Okay. I think we just did question 2. I think it's the same thing. Okay. Okay, now look at the handout. On the handout, we have handout part 1 to question 1. Now question B. Okay, 1B. In question 1B, so do we have the same system? I think we have the same system. Okay. In question 1B, I want you to write the augmented matrix associated with the system. Okay. I think we just did that. Okay. So this is the augmented matrix. So maybe a little bit more comments. Okay. Anybody want to tell me the coefficient of x2 in equation 2? I want to repeat my question. Anybody want to tell me the coefficient of x2 in equation 2? It's missing. It's not written. It's 0. Okay. It's 0. There's a coefficient of x2 in equation 2. We did not see that. We did not write that. So because it's 0. Okay. I'm trying to say in any matrix, it's a rectangular array of numbers that do not miss numbers. In some cases, you have 0. Okay. Okay, I think you know what we mean by augmented matrix already. Okay. Yeah, probably we are going to try one question. Okay. I'm going to add some slides. Probably. Okay, now I want you to try a simple question. Now get a piece of paper, or you can try this question on your notes. We're going to do part 1, question 1A. I call the question part 1, question 1A. Okay. I'm going to put it on PowerPoint. For this question, now open the handout. I want you to read the question. For this question, I want you to write the augmented matrix associated with the system. Again, I want you to write the augmented matrix associated with the system. Try the question for 1 minute, okay, and then we compare the answers. I'm going to write the answer for you, okay. The system has 3 equations and 3 unknowns. Okay. I will give you the augmented matrix. At least you have tried, or you are trying. You keep on trying, then we compare the answer. Okay. Now the answer or the solution to the question. In the question, I'm looking for the augmented matrix. So the solution is, if you have 3 equations, then in the augmented matrix, so there should be 3 rows, right? If you have 3 unknowns, I was trying to say variables. If you have 3 unknowns, then the augmented matrix has 4 columns. So do not forget to include the last column, the column determined by the constant terms. Okay. So maybe you could read to read something for me. Okay, so what's the first row? Read the 4 numbers in the first row. Or you could write it down on the message. 0 is the coefficient of x1 in the first equation, right? And then 0, 1, 1, 3, I think. Yeah, that's the first row. Okay. And then the second row is 1, 1, 3, and 8, right? These are the numbers coming from the coefficients and the constant term. The last row in the matrix consists of, let's say, 2, 1, 6, right? And then 15. Okay. So we have the augmented matrix. A little bit more comments. Okay. For the purpose of solving a linear system, in many cases we use a vertical bar. We use a bar to separate the coefficients and the constant terms. Okay. Okay. That's for the purpose of solving linear systems. You're going to see why later. Okay. Any questions so far? So simple, right? Actually, the matrix of coefficients is a way to represent a linear system. When solving a linear system, we're going to develop a system of systematic ways, okay, in which we need to use the augmented matrix to represent a system. Now look at question 2. Okay, in question 2, it's the other way around. In question 2, I gave you the augmented matrix. If I'm telling you the matrix is the matrix of the augmented matrix of a linear system, I want you to recover the system. So that's the intention of question 2. Okay. So maybe I will show you what I mean using 2a, and then you try 2b. Okay. Now let's do 2a. Okay. Probably it's okay if I copy the entire question on the PowerPoint. Why not? Okay. The requirement of the question is I give you the augmented matrix. Okay. I want you to recover the system. If you could use the xy, x1, x2, x3, and so on for the unknowns. Now let's use xy for 2a. Okay. So in 2a, so the solution to 2a is something like this. I told you that's the augmented matrix of a linear system. I'm sorry, I think I forgot a bar in the question. Okay. So each row determines an equation. Each column to the left of the bar determines an unknown, right? The numbers to the right of the bar determines the constants. Okay. So we have a system of 2 equations in 2 unknowns. Now let's use xy. Okay. So the first equation is going to be x plus 3 over 2 and equals 5 over 2, right? So that's one equation. A system has 2 equations. The second equation is x plus 2y, right? Sorry, I forgot to write y here. X plus 2y equals 3, right? So that's the answer to question 8. Again, you just remember there's a one-to-one correspondence between augmented matrix and linear systems. Okay, I give you a system, you can get the augmented matrix. The other way around, in the other way, I give you a matrix, you should be able to recover the system. Okay. If you want, I can give you 1 minute, 1 minute to do question B, but I think it's too simple. Okay. In question B, so maybe just tell me how many equations in question B. In, for the matrix in question B, it determines a linear system. So there should be 3 equations, right? And how many unknowns? How many unknowns? How many variables? I think 5. 5 variables, right? 5 unknowns. Again, each column to the left of the bar determines a variable, a unknown. Okay. Can we skip that? I think it's too simple. Okay. So very shortly you are going to see the idea. But now let's follow me. Okay. Now let's follow me now. So very shortly you are going to see why we perform row operations. I will tell you the whole picture today even. Okay. To solve a larger system, so what we do is to the first thing we do is to write the augmented matrix of the system, and then the idea is to perform some operations to make the matrix as simple as possible. After we get the simplest form, there is a precise meaning of what we mean by the simplest form. After we get the simplest form, we can get the solution to the system. I know it's too abstract to say that right now, but I will show you the idea. Okay. Okay. Now you need to know the meanings of. You need to know the meanings of elementary row operations. Elementary row operations. Okay. To solve a system, there are 3 operations we can perform on augmented matrices. I want to repeat. To solve any linear system, there are 3 elementary row operations we can perform on augmented system. Okay. The first operation is interchange 2 rows. It's too simple. It's easy. Okay. I will show you the meaning. I think I can just do it on this slide. Okay. The first operation we can perform is to interchange 2 rows. Okay. So now let's say if we have a augmented matrix, something like this. Again, at this point, I'm only telling you what we mean by the operations. Later on, I'm going to tell you how to choose the operations to make the augmented matrices as simple as possible. Okay. But at this point, so do not ask me why we choose the operations. Okay. The first operation is to interchange 2 rows. Now let's say if you have a matrix, augmented matrix, something like this. So now let's say 1, 2, 3, and 4, 5, 6. Okay. For the second row, I'm using a bar to separate the coefficients and the constant terms. Okay. If we perform the operation of interchanging row 1 and row 2, so what's the new matrix? We use arrow to indicate an elementary row operation is performed, and then to get a new matrix. Now listen to me carefully. If I want you to perform the operation of, I want you to perform the elementary row operation of interchanging row 1 and row 2. I think it's super easy, right? You switch the 2 rows. The first row now becomes 4, 5, 6, right? And then the second row becomes 1, 2, 3, right? That's what we meant by interchanging 2 rows. Particularly for this particular row operation, we have a notation for interchanging two rows. In this case, we have interchanged row 1 and row 2, right? We use a notation like that to indicate we are performing the operation of interchanging row 1 and row 2. Okay. It's R1 for row 1, R2 for row 2. Okay. The two-way arrow is for interchanging two rows. Okay. I told you the meaning of operation 1. Okay. The second one is also simple. The second one is it's permissible to multiply a row by a non-zero number. Now I want you to emphasize non-zero number. Okay. If you multiply a row by 0, you are going to have a row consisting of all zeros. That will not, it's not allowed. Okay. It has to be non-zero number. Okay. So how about we just keep on going. Okay. We just keep on going. From here to here, I perform the operation of interchanging row 1 and row 2. Okay. It's also permissible to multiply a row by a non-zero number. Now listen to me carefully, okay? If I want you to perform the operation of multiplying row 2 by -2, what would be the new matrix? Now listen to me carefully. I want to repeat. If I want you to perform the elementary row operation of multiplying row 2 by -2, if I did not mention row 1, then row 1 is not changed. It's unchanged. Row 1 is still 4, 5, 6, right? And I wanted you to multiply row 2 by -2. It means you multiply all the numbers in row 2 by -2. The first number would be -2, right? 1 times -2 is -2. Anybody want to tell me the second number? So just tell me the second number. So I know you are following me. I know it's simple. I just want to make sure.
-4.
Yeah, -4, right? And then you have -6, right? I heard the click. Yeah. Okay, good. Okay. We also have a notation for the operation we just performed. Okay. The notation is the following. The new row 2. Okay. Now listen to me carefully. After performing the operation, the new row 2 becomes the old row 2 multiplied by 2. We use a notation like this to indicate the operation. Okay. You multiply by row 2 by 2, by -2. Sorry, by -2. Okay. You multiply row 2 by -2. That's how you get the new row. And also you include the row 2 in here. Okay. The meaning now is the old row 2. Now listen to me carefully, okay? The old row 2 becomes, you interpret the arrow here as becomes the new row 2 becomes the old row 2 times -2. So I will try again. I know I did not say it super clear, but the meaning of the notation is the new row 2 becomes the old row 2 times -2. Does that make sense? Again, so do not lose track of what we are going to do. We talk about the elementary row operations because we want to use the operations to solve systems of linear equations. The first two operations are easy, okay? And then the third operation is a little bit weird, a little bit complicated, okay? And yeah, probably I'm going to talk about the new operation on the new slide, okay? Okay, now remember the wording. The wording is add a non-zero multiple of one row to another row. I will still try to include everything on this slide. Add a non-zero multiple of one row to another row. Okay. So how about we'll start over. Okay. Now let's talk about a new matrix. So now let's say I do not want to make the numbers too complicated. So now let's say we start from a new matrix. So now let's say 1 1 1. Okay. And then so how about 1 2 3? Okay. I do not want to make the numbers too complicated when talking about the concept. Okay. You imagine that's the augmented matrix of a linear system. Okay. Okay. Now if I want you to perform now water that line. Okay. Water that line when you hear me. Okay. If I want you to add now let's say two multiple of row 1 to row 2. If I add a non-zero multiple of one row to another row, if I want you to add two multiple of row 1 to row 2, which row would be changed? Which row is changed? So give me a little moment. I'm going to write it down. Okay. If I perform the operation of add, so now let's say 3 multiples of row 1 to row 2. It's English, so just read that. So tell me, in the new matrix, which row is changed? The second row is changed, right? The second row is going to be changed. Okay. So the first row is not changed. So after performing the operation, the new row in the new matrix, okay, in the new matrix, the first row is not changed. It's not changed. Okay. And then the problem is you read again. We are going to add 3 multiples of row 1 to row 2. Row 2 is going to be changed. Row 2 is changed. Row 2 is changed. Row 2 is changed. Now we're going to figure out the new row 2. Okay, the new row 2. So to get the new row 2, you do something like this. Okay. You copy this row 1. So row 1, I believe it's 1 1 1. For the first few questions, you could do it on scratch paper. You do not show this. Okay. If you're, I think all of you guys are smart. You could do it mentally. Eventually, I want to be able to do it mentally. But now I'm talking about the meaning. Okay. To get the new row 2, we are going to copy row 1, and then we get 3 multiples of row 1. Okay. So by that we mean we get 3 row 1. 3 row 1. If row 1 is 1 1 1, by 3 row 1 we mean we multiply all the numbers in row 1 by 3. So 3 row 1 is something like this, right? You multiply all the numbers by the idea is to add 3 multiples of row 1 to row 2. Yeah, probably at this point you copy row 2. Row 2 is 1 2 3. Okay. Row 2 1 2 3. Row 2 has all the numbers 1 2 3, right? Now anybody want to write 3 numbers? So tell me the new row 2. We want to add 3 multiples. We want to add 3 multiples of row 1 to row 2. Yeah, 4 5 6. 4 5 6. So we have 4 5 6. You add 3 row 1, row 2 we have 4 5 6, of course. Okay.
ये नहीं आ रहा शाम के फ्री है फोन कर दे ਇਹਨਾਂ ਨੂੰ
Turn off
ਪਾਣੀ
your
ਆ ਗਿਆ
microphone, please. Turn off your microphone, please.
ਤਰ੍ਹਾਂ ਪਾਣੀ ਆਊਗਾ ਤਾਂ ਬੈਠੇ ਰਵਾਂਗੇ ਇਦਾਂ ਹੀ ਉਹ ਬਾਰੇ ਨੋਟਿਸ ਦੇਖਿਓ ਕੋਈ ਉਹਦੇ ਤੇ ਲੱਗਿਆ ਹੋਏਗਾ ਆਪਣੇ ਗੇਟ ਤੇ
So Simran, turn off your microphone, please. Okay, so we have a new row 2, 4, 5, 6. Okay, you know it's 4, 5, 6. At the end of the day, eventually I want you to be able to do it mentally. Okay, now I'm going to show you how to do it mentally. Okay, now we're going to add 3 multiples of row 1 to row 2. Okay, so what you will do is to think from here. 3 times 1 is equal to 3. 3 plus this one is equal to 4. That's how you get this number. Again, eventually I want you to be able to do it mentally. Yeah. So you have 4 in here. 4 is coming from 3 times this number. 3 times 1 is 3, and then plus this one is 4, right? And then 3 times this one is equal to 3, and then plus this 2 is 5. So you have 5 in here. And also you have a 6 in here, right? Again, I really hope you could do it mentally, but if you cannot do it mentally, I showed you how to do that on scratch paper. Okay. Any questions about this? So that's what we meant by operation number 3. Okay. Add 3 multiples of row 1 to row 2. Okay. There's a notation for that too. Now remember the notation. The notation. What I do is always write it backward. We're going to add 3 multiples of row 1 to row 2. Okay. You multiply row 1 by 3, and then you add the multiple to row 2. And then row 2 is changed. We use a notation like this to indicate the operation we just performed. Okay. Now I'm going to tell you the meaning of the notation. The meaning of the notation is here. Okay. Now let's note me carefully. Okay. The new row 2 becomes the old row 2 plus 3 multiples of row 1. So that makes sense? I want to repeat. The new row 2 becomes the old row 2 plus 3 multiples of row 1. Okay? A little bit more comment on this. For the operation we just performed, we are going to agree. You write the operation in that order. I know addition is commutative, but to denote the operation, I want you to write the operation in that order. I'm trying to say, for the operation, so do not use a notation like that. Do not copy. Okay. Sorry. So do not use a notation like that to indicate the operation. I think I was trying to say, so do not use that. I'm going to put a cross sign in here. So do not use that notation. I'm trying to say, always write the operation, the notation for the operation in that order. Okay. So basically, there's one thing you just remember. So this R2 is always the same as that R. Okay. These two notations are always the same, indicating the first row. Okay. This notation, it means the row that is changed. Okay. Any questions about this? Any questions? If you don't have any questions, we are going to do question 2. We have For question 2, I specified the operation, so we're going to perform, and then we use proper notations to do question 2. Okay. I'm going to copy the given matrix. I'll see if I can. Okay, I'm going to try to copy the entire question. It's too big. Okay, do something like this to make it smaller. Okay, starting from that matrix, we are going to perform the operations, the required operations. Okay. Now the solution to that. It's okay. I will divide the whole thing into 2 parts. It's probably easier. Okay. The given matrix you imagine is the augmented matrix of a linear system. The first row is 1, 3 over 2, and 5 over 2. Okay. And then the second row is 1, 2, 3. The second row consists of 1, 2, 3. Okay. In question 1, I want you to interchange 2 rows. To interchange row 1 and row 2 is super easy, right? So because we do not have too much time left, I will go over the solution to that. Okay, interchange row 1 and row 2. Use proper notations. I'm looking for the proper notations. Interchange row 1 and row 2. We have a new matrix, so which is easy, right? Super easy. The first row is 1, 2, 3. You switch to the 2 rows. And then the second row is probably we want to use a bar to separate. We imagine it's the augmented matrix of a linear system. The new second row is the old row 1, so which is 1, 3 over 2, and then 5 over 2. Right? So we're done step 1. In step 2, we multiply row 2 by the scalar of 2. And by the way, by scalar I mean a constant, a number. It's called a scalar. For question 2, we use a notation like this. Okay, we multiply row 2 by a number of 2, So the notation is something like we multiply row 2 by 2, right? And then, so do not forget this part. The new row 2 becomes old row 2 times 2. Okay. I think we have 1, 2, 3. That's the first row. And then the new second row becomes 2 times the old second row. I believe you have a 2 in here. Okay. You have 3, 5 in here. Is that right? Easy, right? I think the first two steps are super easy. Okay. Now in step 3, we are going to add multiple negative 2 of row 1 to row 2. I will do this one for you. You probably want to do the last one. Okay, I will give you a chance to try the last one. We add multiple negative 2 of row 1 to row 2. So basically, we multiply all the numbers in row 1 by negative 2, add the multiple to row 2. So we are having a new matrix. We write the new matrix first. Okay. Now listen to me carefully. So look at my mouse cursor. Okay. We multiply all the numbers in row 1 by negative 2. 1 times negative 2 is negative 2, and then plus 2 is equal to 0. Okay. Sorry, I should have copied the first row first. That number is 0. Okay. Again, 1 times negative 2 is negative 2. Negative 2 plus that 2 is equal to 0. And then the second number in the second row is computed by the following. 2 times -2 is equal to -4, right? So -4 plus 3 is equal to -1. I think -1 is right. Okay. Anybody want to tell me the last number? The last number, please. We add multiple -2 of row 1 to row 2. Anybody want to tell me the last number? Last number, please. Or you can say it. Sorry, it takes. Yeah, it's -1. I will tell how. Okay. -6, and then plus 5 is -1. Okay, so you have a -1 this location, right? Good. That's good. That's good. Easy, right? Still, we need to use a proper notation to indicate the operation we just performed. Okay. You multiply row 1. Actually, I always write it backward. Okay. You multiply row 1 by -2, right? And then you add the multiple to row 2. You do not have to follow me on that. Okay. And then row 2 becomes that. Okay. And the meaning is the old row 2 becomes new row 2 minus 2 row 1. Okay. So we are done 3. I think we are done question 3. And then for question 4, we multiply row 2 by -1. We multiply row 2 by -1. So this one is easy. Multiply row 2 by -1 and then row 2, so becomes that. Okay. Row 1 is not changed. I think you have 1, 2, 3 for row 1, right? And then we multiply all the numbers in row 2 by -1. I think you have 0, 1. So this number is also 1, I think. Now I want you to, I'm not going to give you any hint. Now I want you to read question 5. Give me the 3 numbers. So give me the new row 1. For question 5, we are going to add multiple -2 of row 2 to row 1. So this time row 1 is going to be changed. Okay. Try that for a little while, okay? So just tell me the 3 numbers in the first row. 101 is right. Okay. But I'm going to wait for a little while for other people. Okay. We're going to add the multiple -2 of row 2. I will even tell you the notation. Okay. Row 2 by -2, right? And you add the multiple to row 1. So row 1 is changed. Okay. 101 is right. 101 is super right. 101. If you have 101, then you got the idea, I think. 011. Okay. 011. Okay. So we're done the question. Now listen to me carefully. I will use 5 minutes. I still have 5 minutes. It's not like Math 102. I can do a little longer class, but this one you could have a class at 45, right? Okay. So maybe the whole idea, I'm going to answer the question very shortly. But now let's imagine you're given the augmented matrix of a linear system, and then you perform row operations as indicated, and then you have a new matrix, something like this. Anybody want to tell me the linear system determined by that matrix? I'm trying to say, if I give you augmented matrix, what is the linear system determined by the matrix or associated with the matrix? What is the system determined by the matrix? Again, each row determines an equation, each column determines a variable. How about we just use x, y for the variable? Okay. So just tell me the first equation. X plus 0y. I'm not going to include 0y. Okay. X equals 1 and then y equals 1. Okay. What is that? That is the solution to a system. I'm going to use a few minutes to talk about the whole idea, and then we're going to practice the idea over and over again. Okay. Now let's imagine you are trying to solve a system like this: x plus 3 over 2y equals 4, and then x y equals 3. I know you learned how to solve the system in high school, but now we're going to use the matrix method. Okay. The whole picture, the whole idea, the whole picture. Now the whole picture. Listen me carefully. Given a system, the first thing you do is to write the augmented matrix of the system. Okay. In next class, I'm going to tell you how to choose the operations, and then you perform operations to make the augmented matrix as simple as possible. Later on, we're going to have rigorous meaning of what we mean by the simplest form. Okay, to make it as simple as possible until you have the simplest form. After getting the simplest form, you can get the solution to the system. In this case, we have the solution, right? You can read the solution from the simplest form. X equals 1, y equals 1. That is the solution to the system. This way is better than the way you learned in high school, because this way can handle any system. By any system, I mean no matter how many unknowns, no matter how many equations, no matter how many unknowns, this method is going to be universal. It will apply to any system. It can solve any system. Okay. So that's the whole idea.